So I recently had the idea to try to write an algorithm or program to solve this game Canoodle. So Canoodle, it's a little board game. You have a bunch of pieces and you just try to fill in the board with various shapes. My idea is if I take a picture of the board, I want to have a program tell me this is how you solve this specific configuration based off the picture that you took. So the first thing that I think I need to do is I need to try to have a way to encode a specific configuration. Obviously, this looks like a 2D matrix to me. You know, you have a bunch of these little positions. Each one of those can be indices, right? So that's not too complicated. I think the hard part is knowing how to encode each individual shape. So that's what I'm going to try to implement first, and we'll see how it goes. At this point, I have a JSON file, and each piece, it has like a specific letter, color, and then a shape to it. And then I say what the rows and columns are. So for example, if we had this light blue piece and viewed each piece as a matrix, we can see that it's equivalent to this shape, because anywhere where there's a ball would be a 1, and anywhere where there's not a ball would be a 0. Or looking at this piece, if we were to convert this to a shape, it would be 1, 1, 0, 0, 1, 1, 0, 0, 1. Now that I know the shape of each piece, I need to add logic to set a piece on the board. Nice. It looks like it worked. Each letter is corresponding to an individual piece. So this configuration hopefully should mirror this, what's on this board right now. I think the next part is we need to implement the logic for all of the possible shapes that a piece could have. All right, so I think I have successfully written the logic for creating all of the shapes. So our next step is probably going to be trying to implement the backtracking algorithm. I know I'm going to run into a bunch of bugs because I haven't actually tested any of this, but yeah, we'll test it once we have part of the algorithm implemented. For the algorithm, I'm going to take a backtracking approach because now that I have all of these shapes for each piece, I can just try to add each shape incrementally over the matrix. And if that shape doesn't fit, no problem. I just go to the next shape for that piece and see if that one fits. Once I find a shape that fits for that piece, I just go to the next piece and try to place that shape until the whole board is solved. All right, I tried running it on a very simple configuration, and of course it broke. It's no longer breaking, but the algorithm did not solve anything, so I gotta go back and look at it. Oh, I think I know what it is. So when I'm overwriting the board with the configuration, I am not removing any unused pieces. So essentially it's always trying to add every single piece to the board. So that's definitely the problem, but I guess we'll see. Yesterday, I ran into an issue for 45 minutes trying to understand what was going wrong. I took a look at it today for literally like 60 seconds and I ended up figuring it out. So this is the exact configuration that I provided to the program. And as you can see, there are two pieces that are missing, right? So this would be I piece, and then this would be the K piece. And so as you can see, the program did successfully put the I piece and the K piece in the correct places. Next, I want to test it on a really difficult configuration. So the game comes with like a bunch of different configurations that you can set. I don't know if that's hard to see, but essentially the further you get in the book, the problems get much more difficult. Okay, so this is literally the hardest configuration that the game gives us. So I'm going to input this into the program and I'm going to see if it can tell me how I can solve this. So the backtracking algorithm was able to solve the hardest configuration in 170 milliseconds, which is honestly way better than what I thought it would take. And also I modified the output just to be color coded, and it's easier for me to actually know where to place the pieces now. So the next thing I want to do is I want to try to optimize the algorithm. I want it to be able to solve any configuration in a matter of seconds. And the hardest configuration would be an empty board, right? Because you'd have to add all 12 pieces. I'm not sure how long this would take. I'm guessing it's going to take a while. So if it does, I want to try to find a way to optimize it. So after running the backtracking algorithm on an empty board, it literally took 17 hours and 20 minutes to finish. So obviously there's a ton of optimization that I'm going to have to do to get it down to just a few seconds. But before we do that, let's make sure that this solution actually works on the real board. One idea I have for optimizing is trying to prune some of the decision trees so that we don't have so many recursive calls. I've been playing around with the board configuration. So for this example, you can see that once I place this yellow piece and I continue on placing more pieces, eventually it's going to be determined that it's impossible to solve this configuration. And that's because when I immediately placed this yellow piece in the beginning, it blocked off a section that was only of size 1, which is impossible to now finish because there are no pieces that are of size 1. Another example would be this configuration where this space is blocked off and it's size 3. However, we only have one piece that is size 3 and that's already been placed on the board. So we know already at this point it's impossible to complete this configuration. I don't think implementing this will be very hard, so I'm going to try to add that in and see if it improves things. So my attempt in optimizing the backtracking algorithm completely failed. I ran the extra pruning logic on an empty board and it ended up taking 1 day and 4 hours to complete, which is 7 hours slower than my previous run. Another optimization I'm going to try before Googling stuff is trying to add the larger pieces on the board first. So right now I'm just adding them in the order of their letter, so A to L, but it would be smarter to add the larger pieces first because that would mean the backtracking algorithm has less open spots to check for. So theoretically, it should lead to less recursive calls. It finished in 45 seconds just by rearranging the order in which we add the pieces to the board. So we went from 17 hours to 45 seconds. In terms of how I get this down to just being a few seconds, I'm not sure yet. I'm probably gonna have to Google some stuff. After researching for a while, I think I have an idea of how to optimize the algorithm, but it's gonna be very difficult. What I've learned is that this game where you're placing tiles on a board is what's known as an exact cover problem. I hadn't heard of this term before, but other examples of exact cover problems would be like Sudoku or N-Queens. It's typically used to solve different puzzle type games. I'm sure there are other practical uses, but at least from my research, those are like the most common. There's an algorithm called Knuth's algorithm X, which can be used to solve any exact cover problem. At least for the implementation of this algorithm X, it's done using what's known as dancing links. Essentially, it's a two-dimensional doubly linked list data structure. So it's very complicated. I was reading Knuth's paper that I was able to find online, and I didn't understand really any of it. I read through it all. I'm thinking that this is how we can get the algorithm to run in just a few seconds. All right, so I have the dancing links algorithm implemented, and I was able to run it on a really simple configuration, and it did solve it, but I'm sure there's gonna be bugs on the harder configurations. I'm getting a bunch of Stack Overflow errors on certain configurations. Holy crap, I think it's actually working. It was able to solve this board configuration, which is the hardest configuration that it comes in the booklet, and it solved it in 14 milliseconds. But I guess the real test is the empty board. Oh my God. Okay, it solved the empty board configuration in 20 milliseconds. In the original approach, it took 17 hours. And now with the dancing links algorithm, it solves it in 20 milliseconds. I don't even know what percentage increase that is. I'm gonna calculate that. Okay, so ChatGPT is telling me that going from 17 hours to 20 milliseconds is a 3,060,000% increase. One thing I'm also gonna mention is I would not have been able to implement this algorithm without Knuth's paper. And I also found a GitHub repo going over the Sudoku implementation using the dancing links algorithm. So I referenced a lot of those resources. I did not just code this up all on my own. However, I was able to reuse a lot of the previous logic that I wrote for the other backtracking algorithm. So the next part of this project, I think, is going to be diving into OpenCV and converting an image into an input for our algorithm.
What's your style?
Okay, so I've implemented a testing and normal mode for the program. And this is so that eventually when I write the OpenCV portion, that will be the normal mode where I pass in an actual image. So the image, my idea is I'll pass a command line argument image, and it's just a board with a comma as the delimiter for each row. And so if I enter that, it solves it using the dancing links algorithm, and then it prints out to standard out saying that this is the normal mode and this is the solved board configuration. And so my idea is, since I'm gonna be using Python for OpenCV, I'm gonna use I think it's the subprocess library in Python, and I'll be able to parse this output from the Java program. And for the testing mode, I can set what algorithm I want to use and which configuration I want to solve. So I selected algorithm 1 and configuration 6. And so if I run that, it ran the backtracking with no pruning algorithm on level 6. And as you can see in testing mode, that's when it prints it out all nicely. That's what I've been working on for like the past hour. I've started to implement the Python script using OpenCV, but I've run into a really big issue. Getting the results from the Java program was actually really easy. So the dancing links algorithm is implemented in Java, right? And then I'm using the Gradle package system. So the way I build the command is I just call Gradle w run, and then I specify the arguments. And then the arguments are just normal mode, and then I specify an image, and then I just hard code the image just for testing it out right now. And then I use the subprocess library, pass in that command. I specify capture output equal to true, meaning I want to get the results of standard error and standard out. And then I specify text equal to true, meaning it'll return those results as strings. And then I specify my current working directory, meaning where I want to run this command. And then I just parse the solved board. And as you can see, when I run this, it does return the solved configuration. So that part works just fine. The problem I'm running into, however, is with the OpenCV video capture. So the webcam that I'm using that you can see me with right now is just a USB webcam. And I'm using Windows subsystem for Linux using the Ubuntu distribution. You can even see that in this top part where it says WSL:Ubuntu. WSL does not know of my webcam that's plugged in via Windows. And so this error down here, it's saying that it can't open the camera by index because it's looking for dev/video0, which is in Ubuntu. I thought this would be really simple to fix, but apparently this is a common issue with WSL and being able to use your webcam. After doing some research, I have to download this tool, which will allow me to share USB devices with WSL, but it doesn't stop there. The Linux kernel that's downloaded when you download WSL does not include USB storage drivers. So I have to rebuild the entire Linux kernel for WSL with USB storage drivers enabled in order for me to use the webcam in OpenCV in WSL with the Ubuntu distro. So it's going to be kind of a pain, but that's what I'm going to try to tackle. Okay, so as you can see, I'm successfully drawing these circles on the video capture frames. Now I just need to extract the colors out of this image from these circles. And that's how I will be able to have a correct input to our program. So I'm having a bit of trouble detecting the colors of the pieces, probably because of the lighting in my room. I'm trying to fine tune it and just going one by one, and it is accurately getting some of them. However, certain colors are just really close to each other. You know, like the grays and whites, it's hard to distinguish between them. I think what I'm going to do instead is write a script that will go through a bunch of images that I take in this setting with the lights on in my room and calculate the minimum and maximum value for each piece. Okay, so I ran this tune colors script, which essentially will take a picture of each frame. I update the values for that letter. Hopefully it should be very accurate now. This was the output of the optimized color RGB values for each piece. So I think I know why the color detection has been so inaccurate. I've been trying to detect the colors using BGR, which mixes color and intensity, and that means it's more sensitive to lighting. Instead, I should be using HSV, which will separate the color and intensity. So it's less sensitive to the lighting. I think if I modify it to be in that color format, it'll probably be more reliable. I implemented this automated color tuning in the HSV color space and tested on a few board configurations. Unfortunately, it didn't work at all. It wasn't even able to detect a single colored ball. I was really confused at this point, so I ended up posting on the OpenCV forum and Stack Overflow to try to get some help. I did get some suggestions as to what was going wrong. However, I ended up trying something completely different. Instead of automating the color tuning, I created a small GUI that allowed me to tune the HSV color boundaries manually. This was very time consuming, but it ended up being super accurate. I finally got the color detection to work. It took an insane amount of trial and error. Originally, I was trying to tune the colors programmatically. It just was not accurate. It was not working as expected, and I still am not sure why. I ended up creating this other program involving track bars, and I can move over the HSV values and exactly identify which values to use as my boundaries for each color. So that was the first major change that I made to get this to work. The other major change that I did to get this to work is now I'm looping over every single cropped ball and determining the number of matching pixels for each color. So for example, I have this cropped green ball, and you can see in the output, it corresponds to letter E, and letter E has 73% matching pixels. And there are other letters that do match some of those pixels, but it's not the highest percentage. So I only take the letter that has the highest percentage of matching pixels. So if we go through some of the other ones, G has 74% matching pixels, purple has 69% matching pixels, and empty space has 87% matching pixels. And I do this for every single ball. At this point, I'm like 95% done, I think. I just need to connect it to the Dancing Links algorithm. And then I'm thinking I'm actually gonna draw on the selected image what the correct solution is. All of the code has been written at this point. Now it's time to test it end to end and see if it actually works. And there we go. On the first configuration where I remove just the yellow piece, you can see it actually draws it in. So let's try it on a bunch more. Look at that. I removed 3 pieces, the green, light pink, and yellow, and it did place it correctly. Let's test it on a configuration where there isn't a solution. And there we go. So there isn't a possible solution for this one, so it just draws a red X. All right, now for the final and ultimate test, pretty much the only reason why we implemented the Dancing Links algorithm. Let's see if it can recognize an empty board and return the correct solution. Wow, it did that really fast. This is like one of the coolest things I think I've ever made. Also one of the most difficult. The color detection was easily the hardest part about this project, even more than implementing Dancing Links. If you guys like this video, definitely like and subscribe. I'm planning to build a lot more things this year, so let me know in the comments what else you want me to build. Also, if you're preparing for coding interviews, you can sign up for my newsletter on AlgosWithMichael.com and you'll get 5 completely free, fully animated videos relating to the sliding window algorithm. That's all I have for you guys today. Catch you next time.